Use the first derivative test to find the local minimum and maximum values of g of x equals x over x squared plus 4. To find the critical numbers, we're first going to have to take the derivative. So we're going to need g prime of x, and we're going to use the quotient rule here because we've got the derivative of a quotient. The derivative of the quotient, remember we've got that way to remember low d high minus high d low. So we've got the lower function, which is x squared plus 4, times the derivative of the higher function, the derivative of x is 1, minus the higher function, x, times the derivative of the lower function, which is 2x, all over x squared plus 4, quantity squared. Now, we've got to clean up that numerator. Anything times 1 is itself, so this is x squared plus 4, and then minus 2x squared, all over x squared plus 4, quantity squared. And we can combine like terms in the top, and that's going to give us 4 minus x squared. This is all over x squared plus 4, quantity squared. We can actually factor the numerator. We've got a difference of 2 squares up there. So this becomes 2 plus x times 2 minus x. And we need to know when this derivative is undefined or equal to 0, because that's where our critical numbers are going to occur. Now, it would be undefined if the denominator was ever equal to 0, but this is never going to be equal to 0. X squared plus 4 is always positive. It's never equal to 0. So there are no real numbers that cause the denominator to be 0, which would cause it to be undefined. So we only have to check and see where the derivative is equal to 0. And the derivative is equal to 0 specifically when the numerator is equal to 0. And since it's already factored, that's really helpful. The first factor is equal to 0 when x is negative 2, and the second factor is equal to 0 when x is positive 2. So our critical numbers are going to be positive and negative 2. Now let's set up a sign chart here. We've got negative 2 and positive 2 as our critical numbers. And then we can put all of the factors off to the side. We've got 2 plus x, 2 minus x, and then we can either list x squared plus 4 twice, or we can just write x squared plus 4 squared. Either way, this is always going to be positive, so that makes life a little bit easier. If we look at 2 plus x, this is equal to 0 when x is negative 2. So that's where it changes between positive and negative. And it's going to be positive to the right of that. If you're ever unsure, you can always plug in a number. 0 is a number here, and if we plug in 0, it's going to be positive. 3 is a number here. If we plug in 3, it's going to be positive. And the negative 3 is a number in this interval. If we plug in negative 3, it's going to be negative. So we can see that. And then for the other one, 2 is where it's going to turn between positive and negative. If x is bigger than 2, this is going to end up being negative because we're subtracting something bigger than 2 from 2. That's enough to tip it in the negative direction. But in the other intervals, it's going to be positive. And so at the bottom, we can see that our derivative is going to be negative, positive, and negative. That means the function is decreasing and then increasing and then decreasing. So by the first derivative test, we're going to have a local minimum at negative 2 and a local maximum at positive 2. And we just need to evaluate the function at those values to figure out what those local maximum and minimum values are going to be. So let's start with 2, and I'm just realizing I wrote f, but our function is actually g. Oopsies, sorry about that. Let's see, we know that 2 is going to be a local maximum, so we plug that in. This is going to be 2 over 2 squared is 4, 4 plus 4 is 8, and 2/8 reduces to 1/4. So we have a local max of 1/4 at x equals 2. And if we were to evaluate this at -2, the numerator becomes -2, and the denominator is still 4 plus 4. So this is going to be -1/4. So we have a local min of -1/4 at x equals -2. Those are the local extreme values of the function. And if we were going through to graph this function, we would be able to plot those points and use them to help us create a function that has accurate local maximum and minimum values. And that's what we're going to look at soon, but we also have just a little bit more to look at before we get there.